Hello everyone, Assalamu alaikum. So this is a video on type curves. So type curves, as the name suggests, these are the curves that represent different type of mathematical correlations, but in graphical form. So we see a lot of equations. For example, let me show you some of the equations that I have written here for you. So these are some type of type curves. For example, Rame was a person from India, and he had these equations. He had this equation for porosity. Porosity is like spaces in rock where fluid like is trapped, and then he has this equation for permeability. Permeability is like how much fluid can flow. He had this equation for shut in, like for how much period you can keep the well shut in order to equalize the pressure throughout the well. And then he had storage constant, that how much storage is possible within the rock. And what he did was he just shifted all these equations into a graphical format, which is in form of these horizontal lines. So these horizontal lines represent Raman curves, and these are the actual results of the well. So I think you got an idea what type curves are. These are like graphical representation of mathematical equations, and by using them, you can just decide what type of equations to use for your results of well test. So again, type curves are graphical solutions, same as written here. Uh, they represent equations, and from those equations you can calculate different parameters like permeability, porosity, etc. So use of type curves. Type curves are used for well testing primarily, because well testing have different equations, and an engineer never knows what type of equation to use. So when he has type curves, he can decide what type of equation is best. Because let me show you some of the example. For example, here I'm having a type of a type curve. These straight dotted lines moving upward, and these are actually the well results. So an engineer draw different type of type curves on this uh, semi-log graph, and he saw that these ones were the best matching ones for his actual well results, and he had that whatever the formulas were involved with these type curves, he will use that. So this is how they help an engineer in deciding the type of formulas to use. Again, we try to match the well bore data with the correlation data, and yeah, all that. The best results are used. So these are some of the famous type curves. This is Green Garden. So Green Garden, I always try to understand the origin of the word. So Green Garden is basically, I suppose, an English word, and it means a garden which is green, like greenery. So Green Garden is the name of a person, but its name, it means like something which is green. And there were two people involved in making these type curves. These were actually he and his co-worker Agarwal. Agarwal, again, I think he was from Gujarat, India, probably. Or he was somewhere from India. And again, Agarwal is a name of king in that place. So yeah, and McKinley, I don't know. I have studied what McKinley means, but it's type of card. Rame comes from Rama. Rama is a god in Hinduism, and he was a person, Rame, who was a researcher in petroleum engineering, particularly in well testing, and he developed his curves. Yeah. So now next, these curves are all based on dimensionless variables. Whatever the equations these curves involve, type curves, they are based on dimensionless variables. So dimension basically means that you measure something, and unit is something else. There is a subtle difference between dimension and a unit. Dimension is like you try to measure. For example, length is a dimension. For example, if I have this wire and I try to measure it, how long it is from here to there, it's like 1 feet. I suppose. Yeah, it's 1 feet. So fit is unit, but the length that I measured is not unit. It is the dimension. So in dimensionless variables, we are having numbers, we are having measurements, but we are not having any unit. So there is no problem in unit conversion or any kind of errors occurring due to unit conversions. And in petroleum engineering, mostly we are using, somewhere we are using American systems. So like somewhere we are using American systems, the other we are using, you know, English system, then we are using international SI systems. So when you are using dimensionless system, you do not have to care that what type of unit system you are talking about, because we divide the same quantities, we keep the same quantities in numerator and denominator and make these dimensionless variables, and then we are careless about the unit. Next we have effect of skin and storage. Let me define these both the terms for you. Skin is when there is skin is like a small layer over your skin, right? For example, this is my hand, and this layer, this layer which you can see, which I'm, you know, pushing, it is the skin. It is for example, thin layer over my muscles, and it is consists of fat. Similarly, in the wellbore, it is a thin layer that consists of mud cake and erosion, eroded particles, and you know, salt and other deposits coming due to the small materials coming from the formation with the fluid flow. So skin is this the deposition of these small particles, while storage is uh, the wellbore's capacity to keep the fluid in itself, which is undesirable. It's not good, it's a bad thing to happen. So for example, if you are producing a well, for example, if I am producing this well from here, and this is called sand face, the area where the formation and the wellbore interface exists. So for example, at sand face I am having like um, for example 1000 barrels per day. Okay, you know, the traveling is like 1000 barrels per day, but at surface I am having like 980 barrels per day. So that means 20 barrels every single day are being stored in the wellbore itself, due to due to high pressure they are being compressed in the wellbore, or there is some leakage due to which they are loading in the wellbore, but they are just storing in the wellbore. So it's called wellbore storage. It's an undesirable phenomenon, absolutely. So again, type curves are very beneficial, because mostly the data that we use, for example, if we're using Horner plots for well testing, they get the data has a lot of noise from skin and story, right? And the Horner plots give completely wrong answer. Like sometimes they come completely wrong, otherwise there's a little bit fluctuation and they are not so accurate. Well, you see, Horner plots are not dependent on complete accuracy. But this is a Horner plot; it has specific equations, while the actual well data is like deviating from this line. But we can still deduct that the well data is appropriate for this type curves, and we can use this type the equation from the type curve to solve the problem. So you can see that noise, yes, affects, but they type curves are of such nature that doesn't affect as much. Again, we have they are used in hydraulic fracturing. So these are two wells. This one is before hydraulic fracturing, and this one is after hydraulic fracturing. When we don't have hydraulic fracturing, there are perforations around the wellbore, and when you have hydraulic fracturing, we have enhanced those perforations inside the formations, and then we have perforations like parallel to the wellbore, and the fluid travels from those. So like the interface of the well with the formation increases, like it has more surface area through which it is dealing with. So this changes the fluid flow. This one has more like a radial flow, and when you have fractured and you have increased the surface area, the flow is more like linear. So again, type curves don't get affected by that. Type curves can work on both of these situations. This is an example of type curve for definitely, and they may have different type curves. We have Rame. Rame was an Indian man, and in 1770, I think approximately, he developed these curves. He had his co-worker Agarwal with him, and they were observing a drawdown test. So drawdown means reducing of something, like something is being drawn towards surface or somewhere. So when you are producing the well, you are drawing the pressure from the well, like you are drawing it down or drawing the fluid out. So drawdown is again the pressure, average reservoir pressure minus the flowing pressure. So for example, if the reservoir has 5000 pressure and the fluid that is flowing in the wellbore has the 2000 pressure, so if you subtract the both of them, then we have drawdown, which is 3000. It should be the opposite. Otherwise it should be like 5000 for example reservoir pressure, then 4000 should be the flowing pressure, and 1000 the drawdown is not such big. A drawdown again is a pressure that the well is depleting every single day, with time. So these are some limitations, assumptions taken by him. For example, flow should be constant, the flow shouldn't deviate from its actual value, and there are some more. A reservoir should be infinite acting, so it shouldn't be like reservoir boundaries are being, like reservoir is for example, once depleted, while shut in, it doesn't get to its original pressure. It's like, for example, if this is the boundary of the reservoir and here is the well, so fluid is, and here is the perforation, so fluid is traveling like this, radial flow. Okay, so if this is the boundary of the well and I am depleting it every single day, so after 1.5 year, what we see that the boundary has reduced now, boundary is here. So while at initial conditions the flow was like this, now the flow would be like this. What happens that this area of the reservoir has been depleted by the well which is producing every single day. Well, what would happen if I have an infinite reservoir? Then this boundary which was initially producing the radial flow was like this, right? And even after years of production, this flow would be like this. It wouldn't get like this because the reservoir has an infinite boundary. It doesn't end. So the radial flow is like this, and if you just shut in the well, it would, again, the pressure would equalize throughout the reservoir. So infinite acting reservoir should be there. Once you shut in the well, the pressure should become equalized throughout the reservoir. Again, the same thing. Fluid shouldn't be so much compressible, but again, slight compression is acceptable in Raman curves. So it essentially means that liquids are acceptable because they are somewhat compressible, while gas is highly compressible. So I think it isn't supported by Raman curves. Again, it says a single phase fluid, so we don't deal with two multi-phase flow or two fluids acting at the same time. And then we have it says that homogeneous reservoir. The reservoir should have same rock, same porosity, same permeability, same fluid properties, which we represent by transmissibility. So there is a subtle difference between transmissibility and permeability. Let me explain it to you. So for example, if I am having a rock, like for example, see, this switch is like a rock, right? And it has small pores inside it. So when the fluid travels, due to the linkage of these pores, its permeability. So if the fluid doesn't travel, it means that the pores do not have an interconnectivity between them. While in transmissibility, the fluid flow is dependent on both the rock as well as the viscosity and the mobility of the fluid. For example, if I am dealing with permeability, I am all concerned about this plug, that whether it has connected pores or not. While if I am dealing with transmissibility, I am looking at both of things. I am looking at permeability, whether the pores are connected or not, and I am also looking at how viscous the fluid is. For example, if I flow it through an open channel, then how much it can flow. So transmissibility is like connected to both. It's also related to interconnectivity with pores, and it's also related to how viscous the fluids are. These are the equations used by him. Raman says the porosity is dependent on this constant factor and it increases with the permeability. So for example, you have more interconnected pores, which simply means you are at the first place having more pores. So the more the linkages you have, the more the pores you have, according to Raman. And wherever you see D, so you can see this is PD, this is TD, and this one is also not here, but we have a lot of D, and D stands for dimensionless. So if I am looking at here, it says T upon TD, it means that I'm dealing with dimensionless time. This time doesn't have any unit. PD means dimensionless time, dimensionless pressure. This doesn't have a unit of psi, it's dimensionless. So in the correlations which are used in type curves, most of them do not have units, the factors that are used in them. These are some more formulas that are suggested by Raman. Again, there are hundreds and thousands of formulas. Each curve has its own formula. So yeah, this is an actual example of Raman curves. So these are horizontal Raman curves, and we can see these are actual well bore data. So actual wellbore data after some time of the pressure is increasing. So it means after some time of shut-in, they become horizontal, like they don't change, and they become like parallel to the or collinear to the Raman curves, which means that Raman curves are the best fit for this condition of the wellbore data. Next, we have McKinley type curves, and he has this one formula. It's actually a very big formula, but it is dependent on these factors. So he has on left hand side change in pressure divided by flow rate into formation volume factor. Now this thing is very important. Then what does it mean when you multiply the flow rate by formation volume factor? Again, then we have two conditions. If you are having formation volume factor is like you are converting the volume in the reservoir to the volume in surface. For example, if I am having the volume at the reservoir of the oil, and when the oil comes to the surface, volume naturally reduces. So if I want to get the actual surface volume in Stoughton barrels, but I have the reservoir volume, then I would simply divide it by formation volume factor, because for oil the formation volume factor is more than 1. In mathematics, when we divide something which is whose magnitude is more than 1, then it reduces the value. So if, for example, for oil this is greater than 1, for example it's 2, and we are having the volume, this is actually flow rate. So for example, in sand phase or in the reservoir, the flow rate is like 500 barrel. So at surface it will be like 250, because this is being divided to, you know. And if you are having surface volume and you are multiplying it by formation volume factor, it would again increase it into the volume at the reservoir. So this is the formula used in it. This is an example of McKinley curves. These are in this graph, it's actually an inverse of that one. So it has vertical lines while this one was having horizontal lines. These are wellbore data, and this is McKinley curves. So here they are, getting parallel to the McKinley curves. So this data is most suitable to be used with McKinley type correlations or McKinley type curves. So where can we use it? McKinley type curves can be used to determine flow efficiency. Flow efficiency is basically how much fluid the well can produce with the least amount of drawdown that it causes. Because if your drawdown is very high, if you are depleting the pressure at very high pace, then your reservoir won't last. It would be just, the pressure would be depleted in 2 years, while the recovery would be very low. You would be like depleting the reservoir within 2 years, depleting all of its pressure while you are just recovering, for example, 6% oil. So again, flow efficiency, you can calculate it to his formulas. You can determine transmissibility. I told you about transmissibility. It's both liquid, it's both fluid and rock dependent property. Then we have reservoirs permeability. But we have also Bell's transmissibility and reservoirs transmissibility, because fluid's nature can change depending on the place. You can use it in build up, which means that you are building up the pressure. You have your well shut in drawdown. You are depleting you are depleting your well, and you are drawing the pressure. In fall off test, fall off means you are reducing the pressure. Your pressure is reducing, but it is in an injectivity well, in an injection well. So you have like stopped injecting. It's shut in injection well. So the pressure is falling off because there is no more fluid coming in. And these are useful if your well test is like consists of hours, for example 120 minutes, which means 2 hours. So in that condition this is useful. And again, we have third correlation of or curves. These are Green-Garten curves. So this line, you can see straight line, it represents Green-Garten curves, and these curved lines, you can see these are well data. So you see these well data are most resembling to Green-Garten curves. So I'll be using the equations given by Green-Garten so to solve the parameters that I have to solve about the well. Again, the development is a development by 1979, and it's an upgraded form of Rame's type curve. You can see the Rame type curves are very old, right? Rame type curves were developed in I suppose it was somewhere in 18th century, yeah, 1770. These one were developed in 1770. While if we look at Green-Garten type curves, they were developed in sorry, they were developed in 1979. So it's almost 200 years difference. So these are like the upgraded form of them, and again the same conditions are there as Rame's curves. These are slightly compressed. Use of a slightly compressible, which means liquid, not gas. Homogeneous active reservoir does not have very high changing properties, and there is uniform pressure all around the wellbore. It's not like continuously changing, and they are like reservoirs having no boundaries, infinite acting, constant flow rate. You are flow is not changing. So that's all from my side. These are the type curves, and if you have any question about type curves, you can comment them and contact me on my email. I suppose I have provided them. I have provided you with that. So thank you for watching.